Hi, I'm Alan Weckel from 650 Group, and today we're going to be talking about network, the heart of AI factories, specifically looking at NVIDIA's Spectrum-X Ethernet. And it's my pleasure to be joined today in this fireside chat by Gilad, SVP of Networking at NVIDIA. He actually doesn't need any introductions, but with that being said, Gilad, it's a pleasure to be talking to you again today.
Yeah, likewise.
Cool. A lot has happened so far this year. We're in the early stages of the 800 gig upgrade cycle. Bandwidth is exploding. Scale out is going crazy. We've got scale across these days. Can you kind of ground us in how network architectures are changing within the AI factories?
Yeah, sure. And when we talk about networking architecture or networking architectures, there are actually multiple networking infrastructures that are required in order to build an AI factory. And each infrastructure is different. Each infrastructure needs to support different set of elements. Some elements are common, some elements are less common. The first infrastructure, which is something that we didn't use or it didn't exist a few years back when we were building hyperscale clouds, which is scale up. Scale up, it's a infrastructure that was created for AI, for training, for inferencing, with a mission to connect multiple GPU ASICs and to create a single GPU unit. And it started as a NVLink 8, connecting 8 GPU ASICs to form a single GPU unit. And then it grew up to NVLink 72, and we're talking about NVLink 576, and we're talking about NVLink 1152. So the scale up network is something that is growing in radix, is delivering massive amount of bandwidth, extremely low latency, and of course supporting in-network computing, supporting reduction on that infrastructure itself. So that's a unique infrastructure that was created, and NVLink as a scale up, I believe it is the only purpose-built scale-up infrastructure that exists today. And it's amazing. It's amazing network, and it's a network that actually create a GPU unit. And after we created that GPU unit, we need to scale it out. And when we're talking about scale out networks, a few years back, we used off-the-shelf Ethernet in order to connect the hyperscale clouds. But that technology was built for single server workloads. And therefore, it was important to enable access to servers. It delivers the bandwidth that was required, but it didn't tackle issues of jitter. It didn't tackle issues of multi-process workloads, for example, something that you need for AI, something that you need for distributed computing workloads. And from that reason, we created another purpose-built network. We created Spectrum-X, which is purposely built for AI, purposely built for scientific computing. And its first mission was to eliminate jitter. That's the unique value of Spectrum-X Ethernet, dealing with jitter. And in order to deal with jitter, or to ensure that every GPU unit is completely synchronized with any other GPU unit in a system that can consist of hundreds of thousands of GPUs, we needed to build a full end-to-end infrastructure. And it's a combination of a switch and a SuperNIC that each one of them needs to do different kind of things in order to build that scale-out infrastructure. So it's a completely different than any other Ethernet that existed before Spectrum-X Ethernet. And after we could scale it out, we could also start to talk about scale across and connecting multiple AI factories to form a giant or giga-scale AI factory. And scale across is actually based on the algorithm that we developed for scale out. But what we added is a distance aware. So the algorithms of congestion control or algorithms of adaptive routing have added the capabilities of distance aware. So we can modify them based on distance. And that's enabled us to actually build the giga-scale AI factory. Now, recently, we introduced another infrastructure, a new infrastructure that, again, didn't exist before. And that's our Bluefield context memory storage infrastructure. For inferencing, context memory is growing. We need more places to store KV cache, and we wanted to build something that is very effective, very cost-effective, consuming less amount of power compared to any other storage infrastructure, and leveraging the capabilities of Spectrum-X as well, and the combination of Bluefield 4 as a storage controller, the combination with Spectrum-X, that combination created a new infrastructure, which is context memory storage, for context memory storage. And there is more elements around Spectrum-X, the ability to connect, for example, LPUs or the LPX, the new LPX racks into that AI factory, leveraging a low latency version of Spectrum-X. So what we knew before, or the basis for the Ethernet networks, the off-the-shelf Ethernet networks that existed a few years back, are completely different when we talk about AI factory. From a latency perspective, capacities of bandwidth, in-network computing, jitter, low latency, and so forth. And obviously, there is no one infrastructure that fits all. I already counted 4 infrastructures, and I didn't even touch a secure access network with Bluefield 4 DPUs that also is needed in order to support access of multi-tenant into an AI cloud, for example.
Yeah, and I think that's important because in the old traditional data centers, we had one network, or maybe 2 if we count DCI, and now we're at 4. And the bandwidth, I think you kind of glanced over, but that scale-up network is at least 100x the bandwidth of what we've traditionally seen in compute. So we're talking a tremendous amount of connectivity here, kind of every vector, higher radix, higher speed, and then just raw throughput are far higher in AI than anything we've seen historically.
And it's even the cadence of new releases, the cadence of new technology, the cadence of new switches and new super NICs and new DPUs and storage controllers is amazing. If you look back, I think the cadence between generation was around 3 to 4 years. So you could release a technology, and then you had 3 years to study and develop a new technology that will come later on. In our era, when we're talking about AI, it's every year there is a new platform. Every year there is a new switch. Every year there is a new super NIC. Every year there is a new GPU. The cadence of progress is amazing. If in the past companies could work on one generation, it's not something that you can do today. So you're already working on 2 generations in parallel, and you need to understand what are the technologies that are going to come next. For example, co-packaged optics. And after co-packaged optics, there will be other integration. There is more technologies. So you need to have a very strong research entity, and that's what we're very proud to have within NVIDIA, a networking storage entity that looks ahead and what's going to come in the next 2, 3, and 4 years. An amazing R&D team that works on multiple generations at the same time, and fully working as a single unit, because essentially we're building a single unit of computing, which is the AI factory. It's a single unit that combines the GPUs, the LPUs, the CPUs, the switches, the super NICs, the DPUs, all together to behave like a single unit.
Yeah, absolutely. I track bandwidth every quarter, and it's really interesting to your point of how quickly things are moving. If we look at like any of the recent quarters, we actually ship more bandwidth in one quarter than what we did just 2 years ago, right? So that acceleration and innovation is really highlighted in the data in terms of just how much bandwidth is shipping. You hinted at CPO. So kind of a broader question here. What is changing inside the switch as we move from traditional connectivity in AI factories when we introduce CPO?
Yeah. So in traditional connectivity, if we look on hyperscale clouds, the usage of optical connectivity was not much. Most of the network connectivity was within a rack. So we had a top of rack switch, and then the NICs were connected through copper to the top of rack switch, and then you need to connect the top of rack switch into the outside world, and there was some optics. When we're dealing with distributed computing workloads, when we're dealing with the need to connect within the data center on a scale out massive amount of bandwidth, for example, and then in the future, we're also looking on scale out and the radix is growing and so forth. The usage of optical connectivity is huge. We're using a lot of transceivers and optical engines and lasers and so forth. And it's doubling, just the scale out network, it's doubling from generation to generation, meaning every year. It doubles every year. So the power consumption just on a scale out network is getting close to a 10% of a compute capacity in an AI factory, which is a big number. And as we all know, power is the number one limiting factor when we're coming and building a factory. Power determines how much compute we can place in. And we do want to save power as much as we can. And it's not just on the infrastructure. We are saving power by moving to liquid cooling. We're saving power by moving to hot liquid cooling, so we can save chillers, for example, and save power and have more power dedicated to bring more compute. The infrastructure is no different. We want to save power. And since the optical piece of the network is the one that consumes a lot of power, we wanted to look on how we can save it. And the best way to save power is actually to integrate optical engines with the network devices. The reason that optical network consumes a lot of power is because there is a distance between the network device, the network ASIC, and the optical engine that sits on a transceiver that is plugged outside the box. The distance requires to use power in order to drive data, and this is where you consume power. This is where the power is spent on optical network. By reducing the distance between optical engine that sits on a transceiver, on an outside transceiver, and put that or packaging that together with the switch ASIC, we can save almost 5x the power. And that's actually the minimum power that you can have for optical network. And we know that optical network is a must because we're running long distances on scale out, for example. And that was the reason for co-packaged optics. Now, co-packaged optics, it's not a new concept. It's existed for a few years, and there were multiple attempts to build a production-worthy co-packaged optics. And when we look on co-packaged optics, we wanted to make sure that we build something that is very robust. We wanted to make sure that we're building something that can support large radix switches, and we know that the radix is growing from generation to generation. We wanted to make sure that we are spending the least amount of power, we're saving components, and we also wanted to take advantage of increasing the resiliency of the data center, to increasing the mean time between interrupts, for example. And that was the basis of our co-packaged optics. And it started with designing optical engine based on MRM, for example, micro-ring modulator. It started with working with TSMC to create a new processing, a new packaging process, which is COUPE. Working with other partners of us to build a high-power laser so we can reduce the number of lasers and so forth. There is a huge ecosystem of partner of us that we brought in order to build a production-ready co-packaged optics solution with Spectrum-X. And now it's moving to production. So we're very proud of that. It's not just saving power, almost 5x less power on the optical network. We're also seeing 10x increase in the time or mean time between interrupts. So the resiliency, the reliability of the AI factor is increasing, which is amazing. Those are the two great attributes of co-packaged optics. We have Spectrum-X co-packaged optics is in production. And we will start seeing our customers building their AI factories with co-packaged optics as we enter in the second half of this year.
Yeah, and I think that's an important thing to think about when we go through AI, right? We talk about Ethernet, but we're really reinventing Ethernet for AI, right? What we were doing in the past, you mentioned radix, you mentioned mean time between failures, right? Those metrics on a traditional cloud or traditional data center need to look very different or be improved significantly in order to handle the AI workload. And CPO is one of those enabling technologies as we go on that journey to improving performance. Cool.
Yeah, and that's why we see a lot of excitement around co-packaged optics. Our partners of customers cannot wait to put their hands on co-packaged optics and bring Spectrum-X CPO as their next generation of infrastructure for the next AI factories that they are building.
Yeah, so you hinted a little bit about performance. I've seen some performance metrics on Spectrum-X, and they're very impressive. Can you talk a little bit about what your customers are seeing in real-world deployments?
Yeah, definitely. First, Spectrum-X was built to eliminate jitter. That was number one. As you connect many compute engines together, and we're running a distributed computing workload, which could be a training or could be inferencing, for example, you need to make sure that all of those compute engines distribute data at the same time. They are computing it at the same time. They are sending data at the same time. So they're fully synchronized. The network cannot add delays. The network needs to be jitter-free. The other thing is that we develop capabilities of congestion control to eliminate hotspots, because hotspots create delays on one side, but also hotspots create impact, or they can impact between different workloads or different users sharing the same infrastructure. Meaning, if I'm building an AI cloud and I'm hosting multiple users on them, or actually I can have multiple workloads running at the same time, one workload or one user can impact another user and impact another workload if you don't have the right congestion control mechanisms, for example. And those were the aspects of Spectrum-X. And we saw that in the first installation of Spectrum-X. Spectrum-X was the first one to connect hundreds of thousands of GPUs, 100,000 GPUs in a single infrastructure. Now it's been used to connect hundreds of thousands of GPUs as a single AI factory. The highly effective bandwidth we're seeing immediately. We're talking about 95% effective bandwidth. That's something that was reported. And at the same time, there was zero collisions. Zero collisions on a large networks of 3 tiers of a network back then. When we started, it was zero collisions on 100,000 GPUs. Zero collisions. That's amazing. And when you have zero collisions, it means that there is no congestion. If there is no congestions, multiple workloads can run at the same time, and no workload can impact another one. So the adaptive routing was responsible for the highly effective bandwidth. The congestion control was responsible for zero collisions. And we were seeing reports of very deterministic performance of the network. And in off-the-shelf Ethernet, it's not just the effective bandwidth is slow. It's not just that there are jitters and collisions, but the performance is not consistent. And when it's not consistent, you can not rely on a specific or given performance for workloads. You cannot even provide SLAs if you want to build an AI cloud, for example. And Spectrum-X, the reports were deterministic performance, constant performance, low latency, zero collisions, 95% effective bandwidth. Everything that Spectrum-X was built for, everything that Spectrum-X was designed to deliver.
Got it. So would you say the 95% effective bandwidth is the one thing that stands out the most to you, or do you want to
highlight? Zero collision. I think 95% great, but zero collisions and jitter-free, that's great. This is something that is taking a lot of effort to create, to be able to provide. And that's not something that you can do on a single device. You cannot build an AI network just on a switch. You cannot build an AI network just on a NIC. You need the switch to do things. For example, you don't want the switch to know about data ordering at all. Okay, GPU send data and GPU receive data, and the data that is sent and the data that you receive needs to be in order. But if a switch needs to ensure in-order data delivery, and the switch needs to make sure of distributing traffic across multiple ports, those two cannot work together. It cannot coexist. Either you have the ability to freely distribute the traffic across the entire network that you build, or you take responsibility for ordering. You cannot do both at the same place. And that's why you cannot implement an AI network just on a switch. The same thing also exists on the NIC. That's why we needed to build an infrastructure. And the switch has its own mission, the NIC has its own mission, and obviously those missions needs to work as an end-to-end infrastructure. So that's the secret sauce behind Spectrum X, essentially. And we built the infrastructure, and the reports that we receive from our customers were great. And in my eyes, again, Alan, it's zero jitter. That's the most complicated things to achieve.
Yeah, no, that's impressive. I've seen some of those jitter charts, and it's very, very clean. Can I ask, we don't have any jitter, and we're not dropping packets. So the uptime on these systems has probably improved significantly compared to a year ago. You're nodding your head, so I'll take that as a yes.
And the performance of our workloads is amazing, right? It's like at the end of the day, you want to achieve highly the best AI performance you can get. And that network enables that performance. It's essentially the computing engines are the same computing engines. The difference in how they work together is the infrastructure. If you connect them with an off-the-shelf Ethernet network, it just build a server farm, no more than that. If you build it with a network that was purposely built for AI, you got the supercomputer. And then you get actually the performance the desired performance for the different workloads and so forth. It's all about the infrastructure.
Got it. So on my end, I kind of see the performance gap between those high-end factories, those 100K going to 1 million AI factories as increasing, not decreasing in time. Are you seeing the same thing? Like high-end factories have far higher performance compared to the rest of the industry these days?
So the question is, how do you refer to the rest of the industry? AI or AI, regardless if it's training workloads or inferencing workloads, they require the same thing. They require low latency, they require zero jitter and so forth. So the performance of AI networks, purposely built AI networks, if it's, for example, NVLink for scale up, or if it's Spectrum X for scale out and scale across, or BlueField 4 for this context storage and so forth. That combination of all of those actually create the AI factories that were built for training or inferencing and to enable the agentic AI and so forth. Now, obviously, there is other workloads that are single server workloads, and those are being run on traditional data centers and so forth. And traditional data centers can continue using traditional off-the-shelf networks, which is fine. But for AI workloads, obviously, I see AI factory. Every AI factory can call it an AI factory in that sense. And obviously, we'll see the gap continue to increase versus off-the-shelf networks, off-the-shelf Ethernet, from a matter of bandwidth, from a matter of integration, for example, go package optics, in a matter of supporting more and more complicated workloads and so forth. And remember, even though you have multiple infrastructures, multiple network infrastructures, they all need to work together. They all need to work together because we are building a single unit of computing. So there is connection across all of those infrastructures.
Yeah, absolutely. Can you touch a little bit on some of the pain points you've seen on high-end AI factories that you've already solved? that haven't quite gotten to the rest of the industry yet, or to smaller operators that are a little bit further behind on their journey?
Well, my focus is in AI factory, so that's where my focus is, and obviously, we build things to eliminate jitter, deliver high bandwidth, doing integration of co-packaged optics, and so forth. You can definitely state that in traditional hyperscale clouds, in other data centers that are single server workloads, that most of the data goes between the server and a top of rack switch, then they're gonna run copper. There is no much optics, and they may not use co-packaged optics, for example, and so forth. And they may be good with traditional off-the-shelf Ethernet, which is fine. But our focus is in AI factories. This is what we do. This is what we think. This is what we breathe. This is what we drink. And before I can talk with you about all the stuff that we do there, other data centers that do not run distributed computing workloads definitely can continue and use off-the-shelf networks, off-the-shelf Ethernet.
Okay. And are we seeing a lot of the connection between the two, right? As we get mixture of experts and to a certain extent, agents doing valuable workloads there in the business, aren't they kind of traditional data centers and AI factories talking more and more to each other?
I think that the fact that you have multiple agents and all of them needs to talk with one another do require infrastructure that, again, it's a low latency network. That's one thing. Bandwidth requirement is high, and mixer and experts and agentic AI and so forth. Jitter is always important because those are still a distributed computing workload. It still wants to get answers. It still want to do dispatch of data and collect the data and so forth. It doesn't change. All those AI workload that exist across everything require the same thing. Give me an infrastructure that is built for distributed computing workloads. I need the low latency, I need the bandwidth, and I cannot create delays, or I cannot have one workload impact another. And those are all the things that we built into our infrastructures.
Yep, absolutely. Yeah, we're seeing a pretty big upgrade cycle across the board there to kind of support the existing infrastructure. So that makes sense. Kind of last question here as we wrap up, Gilad. What excites you the most as we look into the second half of 26 and early 27 with Spectrum-X?
It's a good question. The thing is that everything is exciting. Okay, there is no piece of thing that is not exciting. Let's put it like that. Okay, definitely the Verubin infrastructure, Verubin systems going out. Spectrum 6 that goes with that 100 tera switches, for example. The Bluefit 4, SuperNICs, and new context memory infrastructure that we build. Co-packaged optics not going to production, and that's something that people talked about it for several years now. We bring that into a full productions and delivering 10x improvement in mean time between interrupts and saving power. There are so many exciting things as we do, and obviously we're working on the next generation. We're already working on the next generation, and even the generation after that. So there is no dull moment. There is no dull moment. I wish that we could have a little bit more than 24 hours a day. That's kind of a limiting factor. We're trying to wake up 2 hours earlier, trying to gain a few more hours every day. But I think if I need to point something, it definitely co-packaged optics going to production now. It's an amazing milestone. Amazing milestone.
Yeah, absolutely. Yeah, I think the industry has been talking about that for a very long period of time. So kind of seeing it move from the trade show floor to the actual production data centers is a significant milestone.
Yeah, you should see the faces of our folks. We build the CPU systems already inside NVIDIA, and the people that build those systems and operating the systems, you should see how happy they are. Amazing.
Yeah, no, it's pretty cool. Great. Well, I'd like to thank the audience for spending the time with us today. Gilad, I'd like to thank you. I always learn a ton when I talk to you, so appreciate the time that you spent with me today. And with that, we can go ahead and wrap up the fireside chat.
Thank you very much, Alan.